Hello, my name is Anna Barioni. I am a first-year PhD student in the physics department of Northwestern University, and today I want to show you how imperfections can improve laser power. And first, I want to introduce a concept called synchronization. This is a phenomenon that happens when we have a group of individuals and they start to behave in the same way. And usually that happens because the individuals of the system interact and affects each other. And so to give an example of that, we can see that in our very audience. So although I am a theoretical physicist, I would like to invite you all to this short experiment. So I would invite you to give a round of applause. And I want to dedicate that round of applause to science, by the way. But the challenge is, as we start to clapping, I want we all to try to synchronize our clapping so that everybody claps at the same time. Let's do this. Now. Great. We did it. So although we started at different frequencies of clapping, we could all bring our behavior to be the same. And even though we did it consciously by using our hearing and our perceptions, there are many systems that do that spontaneously by their interactions. And this state of synchronization is desired in many systems. And so the question that arises, so if we want to achieve that system, what is the best way? And there's two possibilities that I want you to think about. Would you think that it's easier to get to this state if A, the individuals of the system are similar, exactly the same or very similar, or would you think that it's easier if they have different characteristics? Well, if you answer A, you would agree with the entire physics community until 2019. And it would make sense. It is kind of intuitive to think that if we want that the behavior to be the same, it will be easier if the characteristics are already the same. But it turns out that our research group in 2019 found and published that for some systems, it is optimal to have difference in the individuals in order to achieve that same behavior. And that is a phenomenon that's now called Converse symmetry breaking. And this can be seen in real-world problems. So for example, in power grid networks, where we have a bunch of generators transmitting energy to each other through cables, in that system, the energy losses are minimal when they are synchronized, or when this energy transmitted oscillates in the same frequency. And the best way to achieve that, as my group found out, is if the generators themselves have different characteristics, which can be seen in this picture from the different colors in the dots. So each dot has a different color, and that's the optimal way. And if you recognize, this is actually the power grid system of Germany country. And now my work is to broaden that behavior, that phenomenon, to different systems. So my study focused on laser applications, interacting lasers. And the reason we do that is because many applications, such as sensoring and in Navy applications, we need a larger power. So we want to combine them in a synchronized way to do that. And a cool application that I want to talk about is if we want to develop, for example, a self-driven car. Well, to do that, it's important to map the region around you so you can detect potential barriers and their distance in order to not crash on them. And we can do that with radar sensors, which emits radar waves that travels in the speed of sound. And when they reflect, you can know the distance between you and the barrier. But this could be much more efficient and faster if the wave travels in the speed of sound, in the speed of light, instead of traveling in the speed of sound. And that's where the lasers come into play, because we can have a bunch of, large group of lasers emitting light all the ways, And when they get reflected, there comes the interactions. And we need synchronization to cover, to have large power and cover a large area. So some of my preliminary results already show that phenomenon of converse symmetry breaking. So I want to look at this figure, and this is for as simple as 3 interacting lasers. And identify that there's 2 colors here. Well, blue means that the system is synchronized, and that synchronized state can be maintained, or it is stable. Whereas the red region is the places where the system, the synchronized state cannot be maintained or is not stable. And in this plot, when you are, it shows the difference among the lasers, and the only place where the difference are 0 is the center of this figure where I have a black dot. And guess what? This is the only point where all the lasers are the same. And look at that. It lies in the red region, which is not a desirable one. So if you want to go to the blue region and achieve a stable synchronization, we actually have to introduce imperfections or differences among those lasers. And with that, I want to conclude my presentation by stimulating you to think about how those differences and thinking out of the box can improve many, many systems, and perhaps in the future introduce to you some new and cool technology. Thank you very much.